All right, can everyone hear me? Perfect. Welcome to United Astronomy Clubs of New Jersey. We are here on site in Jenny Jump State Park in Hope, New Jersey. Want to welcome everyone who is not only here on site, but also to our online viewers, because that is right. We do live stream each and every one of these presentations online to both YouTube and Twitch. So if you're ever not happen to be here, I don't know why you would ever not be here on a Saturday night. But if you're ever not here and happen to be looking for something fun to do, you can always join us either YouTube or Twitch and say hi and chat. I love being able to talk to people and answer questions there. You can also go onto our website, uacnj.org. That's where you're going to find a list of all our upcoming talks, as well as talks we have had in the past, and links to those past talks. So if you went, oh man, I missed the talk about the Fermi paradox, I really wanted to watch that, never fear. You can actually go back and see that past presentation. And if you have any questions, put those in the comments. And I do periodically scroll through and try and answer any questions that we see. You can also check us out on our social media pages, our Facebook, our Instagram. We have a Discord server for anyone who is interested in things like that. So we're going to get right into the safety briefing. I give it twice a night for the people here, and it is inescapable. First off, if you need to use the restroom, that is the porta potty in the back to my left, your right. It is illuminated by red for ease of finding in the dark, because that is right, it is dark in a state park. With that being said, any flashlights we have, do try and keep those pointed towards the ground, because we don't need to accidentally start a flashlight rave and blind people needlessly. We also have a little museum area and gift shop. I will be manning the gift shop after the presentation because unfortunately they have not given me the power to be in more than 2 places at once. Once they do that, I got this. But until then, unfortunately, we have to practice some patience. Each of those sheds has a roll-off roof and houses its own telescope. The ones with the roofs rolled off has a volunteer in running that scope. So if you have any questions or about any objects or whatnot in the sky that are up tonight, feel free to ask them, and they'll be more than happy to assist you with that. That being said, when we go to leave, we are using our headlights, because as much as we prefer keeping our night vision, we much more prefer saving money on not having medical bills because we got run over. I am certain everyone here in the United States of America feels the same way about not incurring medical bills. So we will be using our headlights, please. And with that, you haven't come here to hear me blab on and on. So we're going to get into our talk. And tonight's talk is Anatomy of a Star with Paul Fischer.
Don't worry, I'll blab on and on.
But they signed up for you to blab on and on. They didn't do that for me.
They did.
Paul here has a Bachelor in Engineering, Chemical Engineering from Stevens Institute of Technology and has worked in the environmental and chemical industries. Though always interested in the celestial objects, Paul's official start, like many amateur astronomers, was finding himself in the most awkward cold position possible one night trying to find Jupiter and its moons. Once he found him, he was hooked. And through some light reading, I'm using air quotes here, unfortunately it's dark, people probably can't see that, his red list puts my to-be red list to shame. He from there, he has managed to find himself still here volunteering as not only a member of one of our member clubs, Northwest Jersey Amateur Astronomers, but also an active volunteer and our current vice president here at UACNJ. And with that, here's Paul.
Hello, everyone. And a little bit of a mishap yesterday. I did throw my back out, but I do have clean dogs, so that is the bonus. However, as it may look, that we don't encourage you to come onto our lawn. Actually, I'm saying we do encourage you to go around the corner there on our lawn and see some of our members who have telescopes open, as well as visit the observatories. So please do take a look at that after I speak. As Kim said, thank you, Kim, by the way, I am a member of Northwest Jersey Amateur Astronomers, NWJAA, and an observer here at UACNJ. Tonight, the presentation is the anatomy of a star. Before we begin, who, what, and why. So we always go over those things before we dive right into the material. I read The Life and Death of Stars, Kenneth R. Lang, so I recommend that book. And I did a video series, Understanding the Universe, an introduction to astronomy. That's actually a pretty long, great courses. I forget how many, but it was like 7 or 8 DVDs worth of material. I also highly recommend that. Those gentlemen are the experts. I'm an amateur astronomer. All right, so those two people, please credit them with all the good and material, and any mistakes that come across, that blame solely on me. I'm likely the source of the mistake. What are we going to cover? Introduction to a particular star, the inside scoop. Everyone loves an origin story. What makes a star tick? How does our chosen star compare? And then what happens at the end of the story? Introducing the sun. sort of, not really, but the sun's a big part of it. There's a baseline understanding that we need to have about how astronomers do their thing. We do get at, first of all, we do get asked, yes, our sun is a star, and other stars could be considered the suns of their own planetary systems. So sun and star really are interchangeable depending upon the sense that you're using it. However, we must be of two minds when we consider this. When compared with data from and other measurements from other stars, our sun is really kind of average, unremarkable. However, our sun is emotionally, historically, geographically, evolutionarily, and physically indispensable. So our sun is really, really important to us. So we understand the sun is an important thing, but it really is just kind of an average star. We wouldn't be here without the sun. To us, it's the most important star in the universe. That only makes sense, right? It's our home. Now, why did I say sort of? Why is this really a story about something that's different than the sun? Astronomers are actually actuaries. The sun has been around for 4.6 billion years. However, humans have only been around for about 200,000, modern humans. So we haven't seen the sun that long to be able to tell you much about it at all. So how do we know? And when I say we, again, I'm an amateur astronomer, I mean we as a species, as humans. How do we know that how the sun came to be and all those things? Well, when looking at stars outside of our solar system, astronomers not only have to take into account the speed of light and the expansion of the universe, but also their statistical variation. We know that the further we look out into space, the further the light has to travel to us. So if something is, we say, the nearest star is about, say, 4 light years away from us, how long has that light been traveling? 4 years. So we're looking back in time 4 years. So the more we look at stars, the different periods of time any of those stars are in their evolution. Some of them were just born too, and some of them were just born a long time ago. So not only are we looking back in time as we look at the light, we're also looking at the statistical variation of when that star was actually born. So we get a view of many different phases of stars' evolution just by looking at the various stars in the universe. It's not a bug in this case, right? It's not only difficult, I mean it is difficult to take all that type of stuff into account, but it's a feature. It helps us understand the entire evolution of a star. And it works both ways. Not only do we not get a chance to see the sun for a long period of time to understand its entire evolution, but it's close to us, so we get those features from it being close to us, because we can send satellites to it, we can study it from our planet and get a lot of detail and understand the inner workings a lot better than we could a star that we can't travel to as of yet to understand. So our particular star that we're talking about tonight is actually a sun-like model. It's maybe not a stretch to consider it an every star. So when we're talking about the sun, remember that we're getting our understanding both from stars and from the sun itself. So it's a model of an average star, our sun. Don't worry, It's not just going to be a big wall of text that you have to deal with tonight. We're going to talk about, we're going to show you some cool photos. But here's one place to start. If you go to Soho, www.nascom.nasa.gov, or you can just, if you type into your search engine Soho, but include NASA as a keyword also, because if you choose Soho, us here in the New York area know that we will get a neighborhood instead of in New York instead of the sun. So include NASA in your search of Soho, and you will get this website. And I'll show you some pictures, one of which is current as of today. And you want to choose the HMI option. That's what you would get if you were to take your telescope and stick a white, a pretty inexpensive white solar filter on it. Similar to the material that we're all kind of used to at this point from the 2 eclipses that happened relatively recently. But it's designed to be put over a telescope. So here is one, if you notice here, the date, April 2022. And here's one from 2023. And here's ones from 2024. That is, in fact, the 14th of September, so today. What's the difference between this one and then, say, these two? There's a lot more activity, not on this one, which is the 2022, but the 2023 and 2024. That's kind of cool. We're going to go why there's more activity. We're going to go into that in just a little bit. But it is kind of cool to notice that, I know, because we're going to talk about it in a little bit. All right, the inside scoop. What makes up a star? Here's the materials of construction. Very easy. You just take a bunch of hydrogen, helium, and various metals and throw them all together and you have a sun. Kind of easy, all right? So go home. That's tonight's homework project. Everyone go home and make a sun. All right, it's not so easy. In astronomy, metals are any element that is not hydrogen or helium. So basically what astronomers are telling us here, there's hydrogen, helium, and then everything else. Everything else is considered metals to an astronomer. The Big Bang created mostly hydrogen and some helium. They are by far the most abundant elements in the universe. It's more like when it came out of the Big Bang, it was more like an 80 to 20 ratio than it is a 71 to 27 ratio. Metals isn't really satisfying though, right? I said it's everything else. Well, here's kind of cool. This is how we understand what's actually in the sun. This is the sun's spectrum. This is obviously the Roy G. Biv that you learned in school. So this is all the colors of visible light. And these are what are called absorption lines. So if you were to take the light from the sun, split it with a prism, you would notice dim areas on the spectrum from the sun's atmosphere. Now, what are absorption lines exactly? You have gas in the atmosphere of the sun. It is comprised of materials, of hydrogen, a lot of hydrogen, and other things. So you take that hydrogen gas that is absorbing the light from the sun, and when it absorbs light, if you remember about orbitals and all that cool stuff in chemistry, and I say cool stuff because I'm a chemical engineer and I won't let you tell me any different, but you get that light being absorbed by the hydrogen, and remember it kicks as soon as that energy is absorbed by that molecule, it kicks the electron from one orbital up to a higher level orbital. Now, the light was coming towards your eye or towards the spectrometer. However, when that light eventually leaves that molecule, it doesn't have to come back to your eye. It can go off in any other direction. That's what's causing the dimming. The fact that that light is redirected away from your eye off into another direction. And of course, with hydrogen, if you remember, all these orbitals have energy signatures associated with them. So if it gets kicked up to the next s orbital or whatever, and then comes back down again, there is a energy frequency, a light frequency associated with that, and so you get dimming at that specific place. And so scientists looking at that light can tell, oh, these 3 lines, that means it's hydrogen. It's a hydrogen alpha, for instance. And so they know what material is in between the source of the light and your eye, or the spectrometer. That's what an absorption light is, an absorption spectrum is. Here's the abundance of stuff on the surface. This is all your elements along here. I know you can't see the numbers. The numbers don't really matter. This is a logarithmic curve of how much stuff of that material. So this is hydrogen, helium, the first 2 guys on the list, and these are the, you know, the heaviest elements over here. If you notice, hydrogen and helium, like I said in the Big Bang, they're the most abundant things in the universe. Right here, and that's the largest abundance. 2 things are the Big Bang elements. Then you see right here, we have sodium and some other guys down here, and not sodium, but I forget exactly, lithium, I forget, these 2 guys. These 2 guys down here, and these 2 guys, there's no really abundance of them all. So right here, we know we can call these Big Bang elements. Right here, there's something different going on. In fact, they're about at the level of these guys, if you see that. And then there's this series of elements that go down this way. Big Bang. All these at this level here are made by cosmic interactions with gamma rays and things like that. But what's going on here? All these things are made in stars. So 3 different mechanisms there. Cosmic interactions, made in stars, made in the Big Bang. Let's play a game here. Core temperature. This is a mind game. This is a game for yourself. Core temperature of the sun is 1.56 times 10 to the 7th degrees Kelvin. What's something that we know is in Kelvin? That's a mental game you should play. 273 degrees Kelvin is what? 0 degrees Celsius, right. So 0 degrees Celsius or 32 degrees Fahrenheit is, and so that's a lot hotter. Core pressure, 1.97 times 10 to the 11th atmospheres. What atmosphere do we, how many atmospheres do we experience right now here on Earth? 1. A lot of pressure. Look at the mass. 1.9884 times 10 to the 30th kilograms. Oh my. Kilometers in diameter. 1,391,400. The distance from us, 1.496 times 10 to the 8th kilometers. That in miles, that's 93 million miles away. So you want a quick idea of how powerful the sun is? Who's camping tonight here? Raise your hand. You're going to have a fire tonight? How close do you have to be to feel that fire? 10 feet away, right? 10 feet away, you take another step back and it's all of a sudden cold, right? 10 feet. You can feel the sun on your face from 93 million miles away. That's how powerful the sun is, through our entire atmosphere. That distance corresponds to 1 AU. That is, in fact, the definition of what an AU is the distance between the Earth and the average distance between the Earth and the sun. That is 0.000016 light years away. The energy that it puts out, 3.828 times 10 to the 26th watts. All right, again, very, very powerful, insanely. Almost we can't imagine it really, right? But the fact that we can feel it from 93 million miles away, we get a little bit of an idea. It's incredibly hot, incredibly massive, and under gargantuan pressures. It is not made up of matter as we normally experience it here on Earth. It is a fourth state of matter called plasma. Mostly the plasma is made up of hydrogen nuclei, protons, helium nuclei, those are called alpha particles, and free electrons. Plasma is a fluid, even if it is extremely dense at the core of the sun. The average density of the sun is 1.41 grams per cubic centimeter. Does anyone know what, say, the density of water is? It's 1 gram per cubic centimeter. So the average of the sun is 1.41 grams per cubic centimeter. But at the core, it's greater than 10 times the density of lead. So that must mean that other parts of the sun are a lot less dense, gaseous in density. All right, here's what a solar structure looks like. It's made up, our sun is made up of a core, a radiative zone, a convective zone, and then on the atmosphere side of things, it has sunspots, it has the photosphere. That's the last part of the sun that is that you can't see through. So you can't see through the photosphere. It becomes opaque to us at the photosphere. There's a coronal hole there that can happen. There's the chromosphere. That's where we're getting all our colors from the atmosphere from. And there's a flare, sunspot, and prominences that happen either in the sun's atmosphere or above it. So that's our sun and its insides. Oh, and this is important. The interior structure of the sun is revealed by whole helioseismology. It is similar to how geologists use seismology. We know the inside, or have found out more about the inside of the Earth by measuring what? Yes, earthquakes. Thank you for whoever's over in the corner giving all the right answers. So earthquakes actually travel, you can tell by how the waves of an earthquake are bent through the structure of the Earth, on what kind of structure the Earth has as those waves go through the Earth, and where they end up coming out on the other side. So similarly, by observations of the close observations of the sun, they can tell by disturbances in the surface of the sun what's inside the sun. The sun is a magnetic dynamo, and this is where we want to pay attention to why we have more sunspots today than even 2 years ago. Here at solar minimum, we have a kind of a very tidy magnetic situation going on here. The sun has a dipole. What's ended up happening is that the equator, since this is a fluid, a plasma fluid, the equator is actually rotating faster than the poles, and it has this dynamo effect. So if you put a magnet across a copper wire, you end up getting a magnetic and electric field. Same thing's happening here. Since the equator made up of ions is moving slower than the poles made up of ions, it's like holding a magnet to copper and you get a magnetic field. However, since this whole thing is twisting around and coming around again, and it keeps going around and the equator keeps being faster than the poles, then this magnetic field ends up twisting. And over time, that twisting starts really making the magnetic field stretch and bend and twist. And these bends and twists end up being coming out of the sun and creating prominences and creating dark holes and stuff like that on the surface of the sun, because what ends up happening is that material from the sun, from the core cannot end up, or core from deeper in the sun cannot end up coming out to the surface, or does not end up going back in as it normally does, and you end up with cooler material on the surface causing the dark spots on the sun. Now, when I say cooler material, it's still very, very, very hot. It's just not as hot as the stuff next to it. The solar cycle is 11 years long from solar minimum to maximum and then back again. So remember, if you're talking about a period, not only have you to go up and then down, you have to come back again to 0 or whatever your start point was. It was originally discovered by recording the frequency of sunspot activity, flares, sunspots, coronal mass ejections, and coronal holes and other solar surface and atmosphere phenomenon all vary with the solar cycle. It's important to study and predict solar events and the space weather to protect our infrastructure, satellites, and astronauts. Okay, not only is our satellites and our astronauts, which we think about immediately about protecting, but our own infrastructure. Wasn't too long ago where the entire northern east coast was shut down because of a solar event. So we gotta protect ourselves by keeping track of that a little bit. If not for, science. Okay, so how are stars formed? Be very quiet for the next few slides. We don't want to wake the babies. Here's a stellar. This is the Great Orion Nebula. This is the Lagoon Nebula. And when I say this, I mean both of these are the Lagoon Nebula. This is why scientists use and why we have satellites that use other frequencies of light. This is a visual, and this is in infrared. Infrared, we can pierce the dust and actually see the stars. Here's protoplanetary disks. Here are not only the sun, which is a little portion of the center there, but the actual debris left over that is coalescing into planets. Nice. What is a stellar nursery? Stellar nursery is a cold, dense, massive nebula, clouds of molecular hydrogen. Again, molecular hydrogen is most of the stuff in the universe. Cold means about 10 degrees above absolute zero. Massive means tens of light years across. It is protective of disruptive cosmic radiation. That's why it's important that it's that vast, because the cosmic radiation is just pinging around the entirety of the universe, and inside that cloud, beyond layers and layers of intervening gas, is where the stars start to form. Regions can collapse spontaneously if they meet the gene's mass. So there's a certain density of cloud. If we hit that density of cloud inside these stellar nurseries, then on their own, the gas begins to collapse and form a star. Collapse, however, can also be assisted by perturbations from external events, a passing star, nearby energetic event, and cloud collisions, right? Nothing static, nothing is just completely quiescent. Something moves by and causes a wave that causes the gene's mass to be hit, and then boom, stars start to form. A protostar begins to form. A protostar, but it's not yet a star. Protostars are a star heated by gravity collapse, but it hasn't started nuclear fusion yet. Remember the conservation of energy. It's the law. You remember the conservation energy from school. Potential energy gets converted into kinetic energy. The bulk motion of the gas increases. As the things start to fall, that you're moving, that's kinetic energy. That's heat. Enthalpy, heat energy, and pressure energy increases as everything begins to move and collapse. If the protostar is massive enough, eventually hydrogen fusion or burning can be sustained. Burning is an unfortunate shortcut everybody uses. Remember that fusion and chemical burning, for instance, the fires that everyone's going to enjoy tonight at the campsite, two completely different animals. They're not alike. Collapse is halted once fusion kicks off. Hydrostatic equilibrium is reached, and a new star is born. And I put a star by hydrostatic equilibrium because here we have a slide on hydrostatic equilibrium. Plasma pressure pushes out. Gravity pushes in. All right, so you have these gargantuan titanic forces. If you saw those numbers on the in some of the introductory slides, how is that at all stable if we're talking about pressures above billions and conversions of mass in the hundred of millions of tons, with that energy coming out? How is that at all stable? Well, what happens is that a collapsing fluid heats and an expanding fluid cools. So if you have a star and gravity's really trying to collapse it in, and fusion energy is trying to push it out, if somehow there's a little instability and the star collapses just a little bit more for whatever external reason, the star will increase its temperature because you've collapsed it more, right? The enthalpy will increase. The fusion will kick off more and push the star back out again. So it is not only are these titanic forces fighting, but they're fighting in a stable system. And conversely, if something were to expand the star and it were to cool off, then if it were to cool off, what would happen is that gravity would try to collapse it again, thereby heating the star up, and then the fusion kicking off again to its normal level. So that's why it's stable. Changes in the rate of fusion are opposed by the changes in the plasma expansion. Powering a star. What is this fusion thing we're talking about? Why is it different from actual burning, or chemical burning, as opposed to nuclear burning? This is what's happening is you're taking two protons, getting them really close together. The strong force takes over, and you form a helium nuclei, an alpha particle. So what happens is that certain particle, in order to get those two that close together, you have to reach a certain kickoff activation energy. Everything on the kinetic energy, anything moving faster than this line here, will get you that reaction where the strong force takes over and the two nuclei form a helium atom or a helium nuclei. So that's the activation energy here, and this is called a Maxwell-Boltzmann distribution. So this is say the average that you would expect a proton in the sun to a proton nuclei in the sun to achieve, and way over here are the real speedy ones, and the real speedy ones are what end up turning into helium nuclei. However, so that makes a lot of sense, right? That these small amount on the high-end speed side are the ones that end up turning into helium. That makes sense. But sometimes it's really a head-scratcher. There's this thing called quantum tunneling, because if we go back to here and we were to say, hey, this is where the activation energy is, we know because we've done hydrogen fusion, and this is where it ends up being. Well, it turns out that the repulsion force of two helium charged particles, two helium protons, would quash any attempt for fusion to happen. So there's something else going on here. The smallest of matter, remember, behaves quite weirdly. They can behave like waves. Remember, particles, the smallest particles behave both like particles and waves. Small particles can change position without actually moving through space. They can teleport into the new nucleus. It isn't teleportation. It isn't that they decide to go anywhere. It's just that their actual existence isn't necessarily tied to a specific place in the universe. Particles are weird. They're a standing wave phenomenon. They don't necessarily have an exact location in space, and they exhibit, as they get more energetic, this quantum tunneling behavior. The higher kinetic energy a particle has, the more likely it is to tunnel, and quantum tunneling is actually required to make fusion in stars go. All right, then there's the conversion. Also a little bit weird. Remember that the standing energy of particles, E equals mc squared. The amount of energy in a particle is given by its mass times the speed of light. So if you were to convert a particle into energy, whatever that weighs times the speed of light equals the amount of energy you're going to get out. There is 700 million metric tons of hydrogen converted to helium per second in the sun. 700 million metric tons. 5 million metric tons of the matter gets converted to energy per second. So a small portion of that conversion actually gets converted into energy. Some of it doesn't make it to helium. Some of it just gets converted to energy. Remember, so why are we, with those huge amounts of number, why wasn't the sun gone a long time ago? Remember, the sun is 1.9884 times 10 to the 27th metric tons. This number has 27 zeros behind it. This one has a measly, what, 6, 7, 8 numbers behind it. That's why the sun hasn't disappeared on us yet. This number is way, way bigger than this number. There's enough material to go in the sun for it to go another 7 billion years at this rate. So plenty of stuff that we don't have to worry about it. That's some future species problem. All right, so how does this actually happen? And I'm not going to go into detail here, but I will say here's the overall equation. This is the mechanism, and as a chemical engineer, you might think that I find mechanisms cool. I do. That's why this slide exists, but I won't bore you guys with it. But 4 helium protons go to hydrogen protons go to 4 goes to a helium particle plus some gamma radiation and some electron neutrinos. And this is our sun's fusion process in here. And if you can see here, for instance, this 2 hydrogen goes over to here. That's what is called an intermediary, right? So there's some intermediaries that get created and destroyed, and there's multiple steps, but this is how it happens. Other larger stars actually have a different cycle. Larger stars, it ends up being the same stuff being created. However, with the presence of carbon and nitrogen and oxygen, those stars go through the CNO cycle. What determines, and it makes the insides of these stars a little bit different. We won't necessarily go into that either. However, what makes one do one and one do another? Well, whatever path creates if you have 2 parallel paths, whatever one is happening faster is the dominant path. So in our sun, this is the dominant path. In the larger stars, this is the dominant path. So a little arithmetic. I already said this, but we'll go over it again. The atomic weight of hydrogen is 1.0747 grams per mole. The atomic weight that's of a hydrogen proton. The atomic weight of a helium ion is 4.0662602. There's this difference here. I mean, this is what for hydrogen protons add up being. There's a difference between this number and this number. This is made up of 4 of these. This is made up of 4 of these. There's a difference here, however, between these 2 numbers. And that difference, what is missing, is what gets converted to energy and why we have the sun. That is the sun, quote unquote, burning. It's taking that difference in mass and making energy out of it. All right, what do you know from, let's see how I'm doing on time here, doing all right. What we can't know from the light coming from suns. We cannot know the size of stars or their luminosity from knowing their brightness. So brightness is us just standing here on the earth looking at stars. We can't know how bright they are much about them. Light's brightness depends upon the distance. It has an inverse square relationship. So by the square of the distance, the light ends up dropping off by X amount. Stars' brightness are classified by magnitude. Stars' luminosities can be classified by a unit of power like watts or absolute magnitude. So we can't look at a star and say it's so bright because that star is either very bright by itself or it's very close to us. We can't tell. It's close or it's bright. It might end up look exactly the same to us. So this absolute magnitude or some other measurement of its native luminosity is required. What we can know, black bodies from stars are approximate black bodies irradiate with color intensities with a predictable curve. Knowing the curve shape, we can predict its surface temperature, the surface temperature of the star, and knowing the surface temperature, spectral type, and luminosity class, we can know the star's masses. Knowing the star's mass, therefore, lets us know many things about the star, because we know what the star, we can, by looking at the spectra, we can know approximately how big that star is. Knowing how big it is, we know its native luminosity. And now knowing its native luminosity, what can we now calculate? One of the most important things. We know its brightness, we know its luminosity, now we know its distance, because there's an inverse square relationship between a star's brightness and how far it is away from us. So looking at spectra, this is, say, visible light here with these various curves. This is, say, the sun, because look at that. The peak happens to be right in where visible light is. And visible light isn't this universal thing. Universal light just happens to be, that's what our eyes are good at looking at. And our eyes happen to be good at looking at because we were born on Earth. All right? So it makes a lot of sense that our eyes are good at looking at visible light. And so this would be our star. So, so knowing these classes of stars, knowing these dominant lines here, knowing the color of the stars, because we can measure the different peaks of where stars are. The peak of this star is a little bit different than the peak of this star, right? Knowing these peaks, knowing the dominant lines, and assigning a color index to it, we can know the temperature of those stars and start to figure out what those stars are made of, how far away, and a lot of other things about stars. And we give them these classes. Why are these not in alphabetical? We have this. We have everything. All these numbers line up. All these colors kind of line up. You know, in the rainbow configuration. Why do these letters not line up? These letters were assigned back before we knew this relationship. So these letters are legacy, and so they don't make logical sense when we list them out on a chart like this. But they said, oh, we'll call a star that looks like this, we'll call it an O star. And they did all that work, and then they really understood the relationship, but the letters had to be shuffled because of legacy records and all that. Here's some stars that you may have heard of, and Betelgeuse is 19 times more massive than the Sun. Its luminosity is 200,000 times more than the Sun. Its surface temperature, because it is a red giant, is 35,000 Kelvin, so it's a little bit different. Rigel, however, is one on the main sequence. It is 11,000 degrees Kelvin, and it's the 17 times the mass of the Sun. And here's the Sun at 1, 1, and 1, because that's what we're using to define everything. Its temperature is just under 6,000 degrees Kelvin. Just for the record, the Sun is a G2V. The V is a Roman numeral 5. 5 is, the Sun is a G2V, a G25 star. Here's the what's called the Hertzsprung-Russell diagram. So you take all that luminosity, temperature data, and you plot it out on from all the stars that we've observed, and you plot them out on a diagram that looks like this. This is our Sun lies right around there. So when I say it's an average star, it's an average star. Main sequence means that it is burning hydrogen. So this is the main sequence. This is where all the stars burning hydrogen are on the diagram. Here I said, yep, the G2V, that is where the Sun is. Other luminosity classes are up here. This is where our red giants and red supergiants are, up here. And some hyper stars are up here. Also, the white dwarfs appear on this chart here. Just as an aside, they're not burning anything anymore. They're here. So that's what you can do with that data. You can classify all these stars, and up here again are the different types of stars, the different spectral classes of stars. All right, I bid adieu. So do the stars. What will happen to our sun? What is its eventual fate as it starts to run out of hydrogen? When the sun uses up its hydrogen fuel, it'll collapse until its core gets hot enough and begins to fuse helium to carbon and oxygen. More massive stars will repeat this process. Where it stops depends upon its mass. You got hydrogen, helium, carbon, oxygen. It goes all the way up to silicon or concentric active cores found in the massive stars. So the lower you go, the hotter it is, the different stuff that you are creating. So there's concentric cores, one ball located inside another. Successive fusion types require hotter temperatures and give off more energy. The sun or star will expand and become a red giant or a red supergiant. Regardless of mass, you don't go beyond silicon. Regardless of mass, the fusion stops at iron. Iron fusion doesn't happen. It requires more energy to create than in its creation. So fusion stops at iron. Once fusion stops, hydrostatic equilibrium that we talked about is gone. The sun or star will collapse until something stops it. What besides fusion prevents a star from collapsing? Electron degeneracy holds up white dwarfs. Our sun, by the way, will become a white dwarf. It's not big enough to do anything else. Particles with like quantum values may stay separate, must stay separate. That's the Pauli exclusion principle. The free electrons in such a star order themselves in a quantum fashion, not really ordering themselves like a matrix or anything, and provide a back pressure to resist gravity. If electron degeneracy is not sufficient, just under 1.5 solar masses, the star continues to collapse. So if the star is bigger than 1.5 solar mass, the star will continue to collapse past electron degeneracy is not enough, and it'll continue to collapse. Neutron degeneracy then holds up the neutrons, a neutron star. So we're past white dwarf, we're now down to a neutron star. Exactly like electron degeneracy, neutrons are excluded from occupying like states. Neutron stars get an additional assist, however, unlike electrons, neutron stars get an additional assist from the strong force, and it will support between 1.5 and 3.0 solar masses. That's the mass of the remnant. Some of the star can get blown off into space. In fact, many times it is. So the remnant supported is between 1.5 and 3.0 solar masses. And if it's at that size, it'll collapse, and neutron degeneracy will stop it, creating a neutron star. Beyond those two forces, I've got nothing, and neither does the universe. The star remnant will continue to collapse and continue to collapse. And when I say and continue, it's not like it's happening over a long period of time. It happens almost instantaneously and will form a black hole. So I actually have a talk on black holes. So if you want to learn more about that process, go see that, or come see me speaking here about black holes. But here are some pictures of, this is the Ring Nebula, and right in the center is a white dwarf. So the ring nebula is the atmosphere and upper portions of a star blown off into space. The remnant collapsed into a white dwarf. This is the Crab Nebula. Inside here is a neutron star. That star exploded. The remnant created a neutron star, a very dense, much more dense than a white dwarf. Here's supernova nova remnant W49b. We can see the signature of a neutron star or a white dwarf. It gives off some radiation, gives off some hydrogen types and things like that we can identify the fact that those remnants are there. Guess what we can't see in the middle of this? A neutron star or a white dwarf. So guess what astronomers think's in the middle of that one? A black hole. So that is a black hole candidate in the middle of that supernova remnant. All right, everyone, that's it for me. I urge everyone to join an astronomy club, and I would like everyone to stay safe tonight.
All right. Thank you, Paul, for another great talk. So we are going to be doing a question and answer session. I'm sure many people do have questions. I know online had a few. But before that, because I saw a number of you sneaking in after the presentation had already started and after I had done my safety briefing, I must do the safety briefing again. If you need to use the restroom, it is the porta potty in the back to my left, your right. We also have a little museum and gift shop area, which I'll be behind the gift shop desk after the question and answer session, because once again, can't be in two places at once. We do have a few telescopes open. After Paul has put away his computer, he will also be manning a telescope. We did get the roof rolled off for you. So that is good. When we do go to leave, please use your headlights. We prefer not being run over or seeing people get run over or having to fill out paperwork for people getting run over. Let's just avoid that whole hassle. That being said, it is dark. It is a state park. Do try and be mindful to keep any flashlights or cell phones that we might be using to make sure we don't misstep. Keep those pointed towards the ground so that we don't accidentally blind people. All right, so how it's going to work for you guys here. When you have a question, you're going to raise your hand and kind of wave it about and keep your hand up. Because unfortunately I am night blind. I've been looking at a computer screen or my cell phone screen, so everyone's kind of just a shape in the void of darkness. My vision becomes very movement-based, and much like the Jurassic Park T-Rex. So if you stop or put your hand down, you cease to exist to me, unfortunately. Online chat, you have it easy. You just get to type. We'll start this off with our first online question. And Ariana asks, is there a limit to how big a star can get? And I want to know, following that up, is there a limit to how small a star can be?
Yeah, I don't know off the top of my head, but currently in the current state of the universe, yes, there is a theoretical upper limit. I don't know what it is off of the top of my head, but there are suns hundreds, if not a thousand, thousands of times larger than our own sun. So there are much more massive stars in the universe, but there is a theoretical upper limit on how big they can currently be made in the current condition of the universe. However, theoretically, right after the Big Bang, where there was this universe was much different, was much denser, a lot more material packed together. The first generation of stars are, I think, theorized to be even much bigger than what we can make today. But I don't know what the limit is off the top of my head.
And was there a lower limit?
Lower limit, yeah. That fusion burning thing. There are things called brown stars which actually go into that protostar phase. So they, what ends up happening Whoa, boy. Let me see. Hold on. Here we go. I'll get to use that mechanism. I knew I had to include it for some reason. So here, what happens in the protostar is that this step right here, where the deuterium starts to turn into helium-3, this step actually kicks off in protostars before these two steps can go. This is a lower energy step. So in a protostar and in brown dwarfs, they burn. This burns a little bit of but once the deuterium is gone, because there's just a certain amount of deuterium that happens to be in the universe, once that deuterium is gone, those stars are too small to collapse the star further and to kick off those other two steps. So those quote-unquote brown dwarfs don't ever actually become a fusion burning star, and so that is the lower limit. So whatever a brown dwarf is, whatever size that is, and again, I don't know that size just off of the top of my head, that's the limit. That's where you're almost there, but not quite to have a star. Then red dwarfs end up being the actual stars that are the smallest stars.
Right. Was there a question out here? I hear a lot of crickets, which is good since we're in a state park. We're in their home. Anyone? Bueller. Oh, you're hiding behind a post. Like I said, motion activated.
I was curious. I don't know if you went over it. We know the Earth is roughly 4 billion, but the sun itself is obviously older. But how do you determine the age of a star? I mean, how do you know it's 5 billion or 6 billion or 8 billion? What determines the age of a star?
Yeah, where it is on the HR diagram, how much, and from its light, how much fuel it has burned, you can get an estimate. If you know that the star came from the 80%, 20% mix from the Big Bang, and it could have more metals than normal, but it doesn't come off of that 80-20 because that's just what the stuff in the universe is made out of. And you saw our sun is at 71, and what was the other number, 18, something like that. You know, approximately, therefore, this amount of hydrogen has been converted, and therefore an approximate age. That is, I think, one method, but actual astronomers who study such things probably have many other better methods of determining it. So I don't know that off of the top of my head. That's a good question. I'll have to look that one up myself.
I'm sure there's someone out there who would. Well, first, what you do is you cut it in half, then count the rings. The sun is not a tree.
But a conversion coordinate, which we use in, chemical reactions and all that. So some sort of conversion coordinate.
All right. So our next online question, and online people do get those questions in. I know I missed a question last week and I can't find it again. So I don't want to try and avoid having that happen. And I say this now because stream delay is a thing. By the time they get to actually hear that, we've moved on to the next thing. So our next online question is, would a magnet be more magnety near the sun, like the sun supercharges it, or would it be less magnety, where like the sun denatures it?
Yeah, I guess it depends upon, yeah, I'm trying to remember the nature of permanent magnets and how strong of a field that they have to. I remember that they're made by sintering and all that type of stuff, but you can denature magnets by putting them in a strong enough magnetic field. I just don't know how close one would have to be to the sun, but certainly you can get close enough to the sun where that magnet doesn't exist anymore. So at that point, I think the magnetic field would be destroyed. But beyond that easy answer, I can't tell. But yeah, at a certain point, a certain magnetic field would demagnify your magnet. I don't know that you could ever permanently make it stronger, but you can certainly demagnify a permanent magnet.
This just in, when you destroy a magnet, it's no longer magnety. um, questions? Anyone? All right. So if you have a question, like I said, raise your hand, wave it about. We'll move on to our next online question. And is it theoretically possible to save a star from quote unquote dying, or do we have to just get out of Dodge when we know that's going to happen?
Yeah. Our exploration of space and our solar system, we know that we can probably get around in our solar system as a species relatively easily. We're already doing it with unmanned things. We have some major problems to solve still about keeping people alive in longer trips in space, right? There's radiation and stuff in space that's no good to us, and that's one of the big problems about going to Mars right now. However, that's probably a solvable problem for us, and so our current failsafe would be we would, in order to get out of Dodge, we would need to inhabit a body further out in space than the Earth is currently. However, stopping a star, the titanic forces in that, I don't know that the human civilization will be ever capable of influencing the gigantic titanic forces at play inside a star. It's some of the biggest forces in the universe. I don't know that we would ever be able to prevent that from happening. It's not like you can seed it. You would need a star's worth of material to make and why not just transport in another star? But that's all speculative science fiction stuff, and not something that's the physics support that we can actually do.
Right. So I am getting close to the last question, online chat. So I said, do get them in before I end. Any? All right. So our next online question. Why did they keep the legacy letters instead of relettering? Kind of like how they just reclassified Pluto.
Well, first of all, it's good work from very smart people that you don't just want to toss into oblivion, right? You want that historic. Second of all, there's when you have these legacy letters, right? Everyone at the time that they put that chart together and they made the determination to make that chart like that and had the letters out of order, you had 40 years of scientists who learned all the spectral classes that way, and so you would have to inconvenience all the current scientists, and that of course ends up becoming self-perpetuating, because all the scientists who learned it that way now want to use it that way. And so just like anything else where you want to make a societal change, there is a lot of existence from the current society to change it.
All right. So any questions out here? Or do we just have very loud crickets tonight? Very loud crickets. So oh, we got one. Hold on, let me.
When a star fizzles out, does it turn into a black hole, or does it just fade into the?
It depends upon the size. So it can shrink and then stop at the white dwarf phase, like our sun will. If it's bigger, it can shrink, push past that white dwarf phase into the neutron star phase. So some of them do that, all depending upon the size of the remnant left over. And then if it's bigger than that, the neutron degeneracy will not hold it up, and it will shrink down into a stellar mass black hole. Right, that's the making of a star, so that's a cloud of gas that shrinks. That's not the end of the life of a star, so that's the beginning of life. Well, what can happen? What can happen? They won't regenerate, but what can happen is neutron star and white dwarf, neutron star, and black hole mergers. So if those orbits will naturally shed energy due to gravitational waves, and so they will eventually if there's two of them together in one system, they will eventually get closer and closer together and merge. Or if there's a binary companion, what can happen is one's a sun still, one is, say, a white dwarf. That white dwarf can accrue or can accrete enough energy from its sun companion, and it itself can go supernova because it's stolen so much material from its companion. So those things can also happen, and we actually, now that we have LIGO, we can measure those gravitational waves and see them happening. There's something like close to 100 events that LIGO has recorded now, so we've actually seen that stuff happening real time in the universe. And when I say real time, we've seen the gravitational waves as they've hit us, but a lot of them have traveled through space for millions, if not billions, of years. LIGO is
An abbreviation he don't
an
remember.
abbreviation that I'm not remembering off of the top of my, but it's interferometry. It's those things that we're using to measure gravitational waves, and basically it's two tubes about 4 miles one way, and at a 90-degree angles, 4 kilometers one way, 4 kilometers the other way, and they actually measured the length of each of those tubes, so they're very exact. They can tell the different when those the length of those change by a proton in diameter. So they can change tiny measurements, and when they see those things fluctuating back and forth, they know that they've detected a merger event, and so they are measuring gravitational waves. Really sophisticated, sensitive instruments, and really cool stuff that we're doing that now. And they're going to put one of those in space in 10 years or so.
Right. So I want to thank everyone who has joined us. Oh, this is what I said. So, hold on. Let me get you the mic.
Oh, I don't know if it's what you're discussing, but I was wondering by what mechanism does sunlight stimulate melanin or vitamin D production, and why is the differences between, like, say, New Jersey and Florida or the tilt of the sun have that much influence on that mechanism?
Well, that's the strength of the light, right? The more that you are looking down from the sun directly through the top of the atmosphere, the stronger the sun is hitting you. So if you, even during the summer here, the sun isn't all the way at the zenith, is it? It's actually like 41 degrees that way, right? So you're looking through more sun. I mean, looking through more atmosphere at the sun. So less light is reaching you here than in Florida, which is closer to the equator, because this. Well, it makes a difference in our climate, doesn't it? We're cooler than Florida here, so it does make a difference, and it's actually what causes the seasons. People think that we're closer to the sun in the summer and we're further away in the winter, and that's not true. All that's happening is that the sun is looking through. We're leaning into the sun, so the sun's higher in the sky in the summer, and further and lower in the sky in the winter, we're actually, the way our orbit works, and in the northern hemisphere, where we are in the northern hemisphere, we're actually further away in the from the sun in the summer than we are in the winter. It has all to do with how much atmosphere that sun is looking through and how much sun we're actually receiving during a day. So it very much that melanin production. Remember, we can feel the sun hitting us from 93 million miles away. That's creating chemical changes in your skin, and that's what's causing those reactions. I don't understand. You'd have to ask a.
I think
a-
that's a biology,
yeah,
and he's a chemist.
biologist. That. But remember, all these chemical processes, all this stuff, everything on the Earth is basically energized by the sun. Chloroform, the energy production in trees and all plants, it's all chemical reactions. It's all caused by the sun. So it doesn't. So it does make sense that vitamin D is created, a chemical reaction is created by exposure to sunlight.
Yeah, unfortunately, science is a very large topic. That might be a good thing to look up or discuss with like a biochemist, or even your doctor should have some basic knowledge of human.
Well, that's something that I'm now curious about, so I will be looking up that myself when I get home. Good question.
And his to be read list grows longer.
Yeah.
All right. So I think that's it for questions. I do want to thank everyone who has joined us, not only here, but like I said, online. If you happen to check us out on our website, uacnj.org, it has links to all our social media, our online streams, and also our member clubs, because we are a club made up of other clubs. So do check them out. That being said, if you want a completely free way to support us, do hit those likes and subscribe or follow buttons on our YouTube and our Twitch, or just like us over on Facebook or on our social medias. With that, thank you all for coming, and clear skies and better seeing, or good seeing. We're actually good seeing this time.
Thank you, everyone. Have a good night.